Welcome! In this session, we'll tackle problem number 742, closest leaf in a binary tree. We'll explore how to find the nearest leaf node to a given target node in a binary tree. This problem challenges our understanding of tree traversal and pathfinding, so let's dive in and break it down step by step. In this problem, we are working with a binary tree where each node has a unique integer value. You are also given a specific target integer, k, which corresponds to the value of a particular node in the tree. The goal is to find the value of the closest leaf node to this target node. Now, a leaf node is defined as a node that has no children, so it is effectively at the end of a branch in the tree. The distance between two nodes is measured as the number of edges in the shortest path that connects them. For input, you will have the root of the binary tree, along with the target integer k. The output will be the integer value of the closest leaf node to the node with the value k. To better understand the problem, let's look at an example. Suppose the input binary tree is represented as root equals 1, 3, 2, and the target value k is 1. Visually, the tree looks like this. The root node is 1, which has two children, 3 on the left and 2 on the right. In this example, the target node is 1, and the leaf nodes in the tree are 3 and 2, since neither of them has any children. The distance from node 1 to node 3 is 1 edge, and the distance from node 1 to node 2 is also 1 edge. Since both leaf nodes are equidistant from the target node, we can return the value of either leaf node. In this case, the output is 2. Now, consider a second example. Here, the input is root equals 1, 2, 3, null, null, 4, null, 5, null, and the target value k is 3. When visualized, the tree has 1 as the root, with 2 as its left child and 3 as its right child. Node 3 has a left child 4, which in turn has a left child 5. This creates a deeper structure. The target node in this case is 3. To solve this, we identify the leaf nodes, which are 2 and 5. The distances are calculated as follows. The distance from node 3 to node 2 is 2 edges, following the path 3-1-2. The distance from node 3 to node 5 is also 2 edges, following the path 3-4-5. Since 5 is closer in this instance, the output is 5. Let's consider a simpler case in example 3. Here, the input is root equals 1, and the target value k is 1. This tree consists of a single node, which is both the root and the only leaf node. In this scenario, the target node is 1, and since there are no other nodes in the tree, the closest leaf is the node itself. Therefore, the output is 1. Finally, let's summarize the constraints and edge cases for this problem. The number of nodes in the tree can range from 1 to 10,000, and each node has a unique integer value between 1 and 10,000. There is always at least one leaf node in the tree, and the target node k is guaranteed to exist. Some critical edge cases to consider include a tree with just one node, where the closest leaf is the node itself, situations where the target node is a leaf, in which case the output is the target node, and large trees with 10,000 nodes, where efficiency is key. Additionally, if multiple leaf nodes are equidistant from the target node, you can return the value of any one of them. These constraints and considerations will guide the development of an optimized solution. To solve the problem closest leaf in a binary tree, our goal is to find the nearest leaf node to a target node with value k. A leaf node is simply a node that has no children. One approach we can consider is the brute force method. The intuition here is to use a depth-first search, or DFS, to locate the target node k. Once we find it, we perform another DFS starting from this node to calculate the distances to all reachable leaf nodes. The steps include locating the target node first, traversing its subtree to compute the distances to all leaf nodes, and then keeping track of the minimum distance and the corresponding leaf. However, this approach has significant drawbacks. Its time complexity can reach n squared in the worst case, especially for large trees, because we repeatedly calculate distances to leaves. This makes it inefficient. Another option is the graph-based approach. Here, we convert the binary tree into an undirected graph. This transformation allows us to use BFS, or breadth-first search, to find the shortest path to the nearest leaf, since BFS is well suited for traversing unweighted graphs. The graph-based approach is more efficient in terms of complexity. It has a time complexity of n, as BFS visits each node only once, and a space complexity of O, n, for storing the graph in the BFS queue. This method avoids redundant computations and ensures that the shortest path is found due to the uniform weights of the edges. Now, another approach we could consider is the optimized DFS with backtracking. The intuition here is to use DFS to locate the target node while simultaneously recording backtracking paths. After finding the target node, we calculate distances to all reachable leaf nodes both in the subtree and by exploring other branches using the backtracking paths. The steps for this method include performing a DFS to locate the target while storing parent pointers for each node. Then, from the target node, we conduct another DFS to find the closest leaf within its subtree, and finally use the parent pointers to explore other paths that might lead to a closer leaf. While this approach is efficient, with a time complexity of O, n, it does have its drawbacks. Managing parent pointers adds an extra layer of complexity, making the implementation slightly more challenging. After evaluating these methods, we chose the graph-based approach as our strategy. This approach is both efficient and conceptually straightforward. By converting the binary tree into an undirected graph, we can leverage BFS to find the closest leaf. BFS is optimal for this task because it explores nodes level by level, ensuring that the first leaf node encountered is guaranteed to be the closest. This approach simplifies the problem by treating the tree as a graph, where parent-child relationships naturally translate into bidirectional edges. This was the key insight or aha moment that made this approach stand out. Additionally, BFS is particularly well suited for finding the shortest path in an unweighted graph, which aligns perfectly with our goal. When comparing strategies, the brute force approach was discarded due to its inefficiency and repetitive computations. While the optimized DFS with backtracking is also efficient, it introduces unnecessary complexity with its parent pointer management. The graph-based approach strikes the right balance by combining simplicity and efficiency, making it the ideal choice for this problem. The graph-based approach was chosen because it ensures optimal performance with a time complexity of O, n. This method is straightforward to implement and avoids the additional complexity of managing backtracking pointers required in other approaches. Another advantage is that BFS guarantees that the first leaf node encountered during traversal is the closest one, which eliminates the need for any further calculations. By converting the binary tree into an undirected graph, we simplify the problem while maintaining efficiency and correctness. Overall, this approach offers the perfect combination of simplicity, performance, and clarity, making it the best solution for solving the closest leaf in a binary tree problem. The problem we're tackling here is to find the closest leaf node to a given node k in a binary tree. A leaf node, as a reminder, is any node that doesn't have children. The distance between nodes is defined by the number of edges in the shortest path connecting them. Our task is to determine which leaf node is closest to the target k and return its value. To solve this, there are a few important insights we need to consider. First, we'll need two types of traversals. One will help us locate the target node k in the tree, and the other will compute distances to find the closest leaf. Second, while a binary tree is hierarchical, we can also treat it as an undirected graph by adding edges between parent and child nodes. This approach allows us to calculate distances more flexibly. Finally, our focus will be on identifying leaf nodes during traversal, as they are our key targets. By definition, a leaf node does not have left or right children, which will be a helpful condition during our traversal. To achieve this efficiently, we'll use three primary data structures: a dictionary to represent the graph, a queue for breadth-first search, and a set to track visited nodes and prevent infinite loops during traversal. To solve the problem, we'll break it down into a series of steps. First, we need to build a graph representation of the tree. This involves traversing the tree using a depth-first search and adding bidirectional edges between each node and its children. This step effectively converts the tree into an undirected graph. As we construct the graph, we also identify the target node k by checking if we encounter its value during traversal. At the same time, we'll identify all leaf nodes by checking for nodes that lack both left and right children. Once the graph is built, the next step is to perform a breadth-first search starting from the target node k. We initialize a queue with k and set the starting distance to 0. As we process nodes in the queue, we'll use a set to keep track of visited nodes, ensuring we don't revisit nodes and create loops. For each node, we check if it's a leaf node. If it is, we immediately return its value since BFS guarantees that it's the closest. If it's not a leaf, we enqueue all unvisited neighbors of the current node while incrementing the distance. This process continues until we find the closest leaf node, which will be returned as the result. Now, let's translate this algorithm into pseudocode to see how it works step by step. First, we define a function to build the graph from the binary tree. We use a helper function that performs a depth-first search, starting from the root. For each node, we add it to the graph as a key, and if it has a parent, we create bidirection ledges between the node and its parent. We then recursively process the left and right children of the node. Once the graph is built, we switch to the main function that finds the closest leaf. Here, we initialize the graph using the helper function, then set up a queue with the target node k as the starting point. We also initialize a set to track visited nodes. As we process nodes from the queue, we mark each as visited. If we encounter a node that has only one connection in the graph and it's not the root, we know it's a leaf node. In that case, we return its value immediately. This approach ensures that we find the closest leaf as quickly as possible, leveraging the level order nature of BFS. To complete the BFS, we loop through the neighbors of the current node. For each unvisited neighbor, we add it to the queue, ensuring that we expand our search outward from the target node. This guarantees that the first leaf node we encounter is the closest. Let's now analyze the algorithm's complexity. The time complexity is O(n), where n is the number of nodes in the tree. This is because we construct the graph in O(n), and the BFS visits each node once. The space complexity is also O(n), as we need space for the graph representation and the BFS queue. Finally, let's consider some important edge cases. If the tree has only one node, that node is the closest leaf to itself. If the target node is already a leaf, the algorithm will return it immediately without further traversal. For deeply nested trees, the BFS approach ensures efficiency by exploring level by level rather than diving into one branch. These considerations make the algorithm robust and well-suited to handle various tree structures. Here, we begin implementing the solution for finding the closest leaf in a binary tree. First, we import the necessary modules, defaultDict for creating the graph representation of the tree and Deek for the breadth-first search traversal. Then, we define the main class solution and its method findClosestLeaf, which takes in the root of the tree and the target node value, k. Within this method, we set up a helper function, build_graph, to convert the binary tree into an undirected graph. Each node in the tree is connected to its parent and any children it has. This structure helps us efficiently traverse the tree in any direction. The function recursively traverses the tree, adding edges between the current node and its parent, as well as between the current node and its left and right children if they exist. This recursive approach ensures that the entire tree is processed into the graph. Additionally, we define another helper function, BFS_closest_leaf, which will perform a breadth-first search to locate the nearest leaf node. To start, we initialize a queue with the given starting node and a set to track visited nodes. This ensures we don't revisit nodes unnecessarily during the traversal. The breadth-first search continues by dequeuing the current node and checking its neighbors. If a node has only one connection in the graph and is not the root, it qualifies as a leaf node, so we return it immediately as the closest leaf. Otherwise, we iterate through the neighbors of the current node. For each neighbor that hasn't been visited yet, we mark it as visited and enqueue it for further exploration. Once the graph is built using the build_graph function, we initialize it as a defaultDict of lists to store the connections between nodes. Finally, we call the BFS_closest_leaf function, starting from the target node k. This ensures that the search begins at the specified node and finds the closest leaf efficiently. The result of this function is then returned as the output of findClosestLeaf, completing our implementation. Here, we start with the Java implementation of the solution. The goal is to find the closest leaf node to a given node in a binary tree, where the value of the target node is k. We use a graph-based approach to solve this problem. The findClosestLeaf method initializes a graph as a hash map, which will represent the tree in an undirected graph format. Then, we call the buildGraph helper function to convert the binary tree into this graph structure. Each node and its relationships with its parent and children are stored as entries in the graph. Notice how we handle the tree traversal. If the current node is not null, we add it to the graph, and if it has a parent, we establish a two-way link between the node and its parent. This ensures that the graph is bidirectional, allowing us to traverse both upwards and downwards in the tree during the search. The recursive calls to build graph ensure that the entire tree is processed, including the left and right subtrees of each node. After building the graph, the BFS-defined closest leaf method performs a breadth-first search, BFS, to locate the closest leaf node. We initialize a queue to manage the BFS traversal and is set to keep track of visited nodes to avoid cycles. The BFS starts from the target node, represented by the start parameter, and we add it to both the queue and the visited set. During the traversal, a node is identified as a leaf if it has exactly one neighbor in the graph and is not the root node. If we find such a node, we return its value immediately, as it is the closest leaf. Otherwise, we continue exploring its neighbors, adding unvisited ones to the queue and marking them as visited. The BFS ensures that we process nodes level by level, guaranteeing that the first leaf we encounter is the closest. The return value of -1 at the end is just a safety measure and should not be reached since the problem guarantees the existence of a leaf node. Finally, we have the definition of the treenode class, which represents the structure of a binary tree node. Each node contains an integer value, as well as references to its left and right child nodes. This class is used to model the input tree passed to the find closest leaf method. The constructor initializes the node with its value while leaving the left and right child references null by default. This simple structure allows us to represent any binary tree and serves as the foundation for building the graph representation in our solution. To solve the problem, we start by converting the binary tree into an undirected graph. This allows us to perform a breadth-first search efficiently. Looking at the tree structure, we begin at the root node, which is 1. Since there's no parent for the root, we don't add any edges yet. Moving to the left child, node 2, we create a bidirectional edge between nodes 1 and 2. Similarly, for the right child, node 3, we add edges between nodes 1 and 3. Now, node 2 has its own left child, node 4, so we add edges between nodes 2 and 4. At this point, the graph representation is complete, and it looks like this: 1, 2, 3, 2, 1, 4, 3, 1, 4, 2. With the graph built, we proceed to perform a breadth-first search starting from the target node, which is k equals 2. We initialize our queue with the target node, q equals dec, 2, and the visited set is 2, to keep track of nodes we've already processed. Dequeuing node 2, we check if it's a leaf. Since it has neighbors, it isn't. We then explore its neighbors, nodes 1 and 4, adding them to the queue and marking them as visited. The queue becomes dec, 1, 4, and the visited set is 1, 2, 4. Next, we dequeue node 1. It also isn't a leaf, so we explore its neighbor, node 3, adding it to the queue. The updated queue is dec, 4, 3, and the visited set is 1, 2, 3, 4. Finally, we dequeue node 4. Since it has no neighbors, it's a leaf, and we return node 4 as the closest leaf to the target node. Thus, the output is 4. Now let's consider a more complex tree where the target node is k equals 3. First, we build the graph as before. Starting at the root node, we create edges between nodes 1 and 2, and nodes 1 and 3. Moving to node 3, we add edges for its children, nodes 4 and 5. Node 5 has its own child, node 6, so we add edges between nodes 5 and 6. The final graph representation is 1, 2, 3, 2, 1, 3, 1, 4, 5, 4, 3, 5, 3, 6, 6, 5. Next, we perform BFS starting from node 3. The queue is initialized as dec, 3, and the visited set is 3. Dequeuing node 3, we see it isn't a leaf, so we explore its neighbors, nodes 1, 4, and 5, adding them to the queue. The queue becomes dec, 1, 4, 5, and the visited set is 1, 3, 4, 5. Dequeuing node 1, we find it isn't a leaf. Then, we dequeue node 4. Since it has no neighbors, it's a leaf, and we return node 4 as the closest leaf to the target. Thus, the output is 4. Finally, consider the simplest case of a single node tree, where the root node is also the target, k equals 1. Here, the graph representation is straightforward, 1, as there are no edges. Performing BFS, we initialize the queue as dq, 1, and the visited set is 1. Dequeuing node 1, we check if it's a leaf. Since it has no neighbors, it is indeed a leaf. Therefore, we return node 1 as the closest leaf. The output is 1. In this problem, we have two main steps that contribute to the time complexity: graph construction and BFS traversal. First, during graph construction, we use a depth-first search to traverse the entire binary tree. For each node, we process its value and add edges between the current node and its parent, left child, and right child. Since we process each node and edge exactly once, the graph construction step takes n time, where n is the number of nodes in the tree. Next, we perform a BFS starting from the target node k. The BFS explores the graph layer by layer, visiting nodes until the closest leaf is found. In the worst case, where the tree is unbalanced or forms a single path, the BFS may visit all nodes and edges once, which also results in n time. Therefore, each step individually has a time complexity of n. Now, when we combine both steps, the total time complexity becomes n for graph construction plus n for BFS traversal, resulting in n overall. For space complexity, the graph is stored as an adjacency list using a default dict, where each node points to its list of adjacent nodes. In a binary tree with n nodes, there are n nodes and at most n1 edges, with each edge stored twice due to bidirectional mapping. This means the graph representation requires n space. Additionally, the DFS used in the graph construction has a call stack depth equal to the height of the tree. For a balanced binary tree, the height is log n, while for a skewed tree, it's n. In the worst case, the recursion stack contributes n space. Therefore, these two factors together give a space complexity of n. The space complexity also includes the BFS queue and visited set. The BFS queue holds nodes to be processed, while the visited set tracks nodes that have already been visited. In the worst case, both the queue and the visited set may store all n nodes, contributing another n to the overall space usage. Combining the graph representation, DFS call stack, BFS queue, and visited set, the total space complexity remains n. Now, if we analyze the best, average, and worst cases, the best case occurs when the target node k is already a leaf. Here, the BFS terminates immediately, so graph construction still takes n, but BFS only requires 1 time, resulting in n overall. The space complexity remains n due to the graph storage. For average and worst case scenarios, such as balanced or skewed trees, the BFS may explore the entire graph, leading to a time complexity of n and a space complexity of n. When we compare our approach to a naive method, the differences become clear. A naive approach would involve recursively calculating the distance to all leaves from the target node. This could lead to traversing the tree multiple times, as each node would compute distances to its respective leaves. For n nodes, this approach could take n time per node, resulting in a total time complexity of n squared in the worst case. In contrast, the proposed graph-based approach processes each node exactly once using DFS for graph construction and BFS for traversal. This ensures a linear time complexity of n. The significant reduction from n squared to n makes our method much more efficient, especially for large binary trees. Finally, let's solidify our understanding with a mathematical proof of the big O complexity. During graph construction, every node and edge is processed exactly once, resulting in n operations. Similarly, during BFS traversal, each node is enqueued and dequeued once, while every edge is checked once, leading to another n operations. Combining these two steps gives a total time complexity of n plus n, which simplifies to n. For space usage, the graph representation requires n space, and the BFS queue and visited set also require n space in the worst case. Together, these dominate the overall space complexity, which is n. Thus, both the time and space complexities of the solution are n, making it highly efficient. When approaching this problem, there are a few common mistakes to watch out for. One major pitfall is assuming the tree is a binary search tree, or BST. Unlike BSTs, a general binary tree does not have any specific ordering of its nodes, so relying on properties like left or right subtrees being ordered can lead to incorrect traversal logic. Another mistake is not accounting for disconnected paths when converting the binary tree into a graph. Remember, you need to account for edges between parent and child nodes to ensure your graph representation is complete. Missing these connections will lead to faulty results. Inefficiency is another concern. Some solutions involve performing a depth-first or breadth-first search from every node, which can lead to redundant computations, especially for larger trees. Instead, you want to use a strategy that minimizes repeated work. Finally, don't overlook edge cases. For example, if the root itself is the target, or if the tree has just one node, you need to handle these situations carefully to avoid errors in your solution. Another common issue is overcomplicating the solution. Some candidates introduce unnecessary complexity, like using priority queues, when a simple breadth-first search is sufficient for finding the shortest path. Now, when it comes to solving this problem effectively in an interview, converting the binary tree into an undirected graph is a critical insight. This transformation allows you to leverage BFS for shortest path determination, which is ideal for this kind of unweighted graph problem. Additionally, this challenge is a great test of your ability to adapt your tree traversal knowledge to a graph-based context. Understanding how to maintain relationships during data structure transformations is a valuable skill. In terms of performance, an optimal approach has a time complexity of O(n), where n is the number of nodes in the tree. Using BFS with an adjacency list for the graph ensures this efficiency. Finally, clear communication is key. Always explain your reasoning, especially why BFS is the right choice here, as it guarantees the shortest path in an unweighted graph. This problem is closely related to others on LeetCode that you might find helpful to practice. For example, LeetCode 863, which asks you to find all nodes at a certain distance from a target in a binary tree, uses a similar graph transformation and BFS strategy. LeetCode 112, which deals with path sums, focuses more on tree traversal, though the concept of exploring paths is still relevant. Another related problem is LeetCode 111, which requires finding the minimum depth of a binary tree, a task that also involves identifying the nearest leaf, though without a specific target node. Now, in terms of alternative approaches, one option is to stick with pure tree traversal and use a depth-first search to calculate the distance to the nearest leaf for every node. Then, you perform a second DFS to locate the target node and its closest leaf. However, this method can be less intuitive, harder to explain during an interview, and often involves revisiting nodes unnecessarily. The preferred approach is to convert the tree into a graph and solve it with BFS. While this requires some upfront work to construct the graph, BFS ensures an optimal and straightforward solution. This clarity and efficiency make it the better choice in most scenarios, especially in interviews. Great job! In this session, we explored the closest leaf in a binary tree problem, where we used BFS to efficiently find the nearest leaf node. We reviewed key takeaways like the importance of BFS and converting trees into graphs for certain problems. Thanks for watching, and be sure to stay tuned for more exciting content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!